students. Today I'll be talking about two interesting phenomena occurring during photosynthesis. These are the oxygen evolving complex, how it helps in evolution of oxygen, and the Quinone cycle, which helps in the production of protonmotive force, which in turn helps in the production of ATP, occurring in the or during the light reactions of photosynthesis. Photosynthesis comprises of two distinct phases: the light reactions, as the name suggests, which occurs during the daylight, and the dark reactions, which occurs in the dark. So it was assumed that the dark reactions occurs in absence of light. But now it is very well known that the light and dark reactions, they go simultaneously. So during the light reactions, there is an electron transfer, and these electron transfer are initiated from photosystem 2 to photosystem 1. So this is represented in the form of Z scheme. So what is Z scheme? Z scheme is basically the electron transport chain of the flow of electrons which is occurring between the two photosystems with the help of mobile electron carriers. So let us now, the Z scheme which occurs in oxygenic photosynthesis. So Z scheme comprises of two photosystems. These two photosystems, they act in tandem to catalyze the light-driven electron transfer from water molecules to NADP+. NADP+ is the electron acceptor and water is the electron donor. It is referred to as Z scheme because of its overall form. It resembles the letter Z sideways, and it outlines the path of electron flow between the two photosystems and the energy relationships occurring in the light reactions. So let us now come to how many photons of light are required for this electron flow from water to NADP+. So the Z scheme, as I told you, it initiates the electron flow. So if you look into the energy requirement, it requires 8 photons of light to transfer 4 electrons from 2 molecules of water, 2 molecules of NADP+. So there are 8 photons, 4 photons absorbed by each photosystem. That is 4 photons absorbed by photosystem 1 and 4 photons absorbed by photosystem 2. So the reaction is 2 H2O plus 2 NADP plus 8 photons is giving you 1 molecule of oxygen plus 2 NADP plus 2 H plus. So this is the net reaction of the Z scheme. So this is the formula, or this is the structure or the simplified diagram of Z scheme, where the light falls on photosystem 2 and photosystem 1. The light absorption by photosystem 2 and photosystem 1 initiates an electron transport chain, and this electron transport chain ends up in the production of NADPH. NADPH is a strong reducing molecule, and it is used in the dark reactions of photosynthesis. So let's move further. Let's break down the structure of Z scheme, or see what is the physical and chemical organization of Z scheme. So the chemical organization or the physical organization of the Z scheme, which is the major electron transport chain occurring in the light reactions, are majorly carried out by 4 protein complexes. These are photosystem 2, cytochrome B6F, photosystem 1 and ATP synthase, mentioned sequentially in the order of their function or in the order of electron flow. Let us come to their individual function. Photosystem 2, that is, it helps in the evolution of oxygen. It is majorly concerned with the evolution of oxygen, as it contains the oxygen evolving complex associated with it, present on the luminal side of the thylakoid membrane. So photosystem 2 produces reduced plastoquinone. The reduced plastoquinone then diffuses into the hydrocarbon chain of the membrane, and it passes on to the cytochrome B6F complex. The cytochrome B6F complex which is a multi-subunit complex, accepts the reduced plastoquinone, oxidizes it, and the famous Quinone cycle occurs here. It is during this Quinone cycle, known as Q cycle, the translocation of protons takes place across the membrane. The translocation of protons from the stroma to the lumen takes place during the Quinone cycle. The electrons are then passed to photosystem 1 through plastocyanin. The photosystem 1 again initiates the electron transport, that is, the electron charge separation event takes place, the electron transport chain takes place, and then it produces NADPH. This NADPH is then used in further downstream reactions. The translocation of protons across the thylakoid membrane, that is from the stroma to the lumen, produces a chemical and an electrical gradient of protons, which is known as the protonmotive force, and this protonmotive force is utilized by the ATP synthase complex to produce ATP. So, this is how ATP and NADPH are produced during the light reactions of photosynthesis. So, what are the end products of light reactions? These are ATP and NADPH produced in a definite ratio. Now, if you look into the physical organization of the Z scheme, besides the 4 protein pigment complexes, there are other electron carriers as well. There are 2 electron carriers, that is plastocyanin and plastoquinone. Plastoquinone accepts the electrons from photosystem 2, gets reduced, whereas plastocyanin carries the electron from cytochrome B6F to photosystem 1. So, this is how the physical organization of the Z scheme looks like, which is the scheme of electron transfer during the light reactions. Now, if you move forward to the electron transfer reactions occurring in photosystem 2. Photosystem 2 reaction center, if you look into the diagram or into the figure, you will find that there are 2 light harvesting complexes, CP47 and CP43. These capture the light energy efficiently, pass it towards the reaction center. In the reaction center of photosystem 2, there is a special pair of chlorophyll A molecules known as P680. P680, that is the chlorophyll molecules which absorbs photon of light at 680 nanometer. After absorption of light energy, they undergo an electron transfer reaction. That is, after absorption of photon of light, they have a lower reduction potential. As a result, they give away their electrons to Phaeophytin. Phaeophytin is a chlorophyll molecule without the magnesium atom. The Phaeophytin, after it accepts the electron from P680, it becomes negatively charged and then transfers the electron to PQA, that is a quinone molecule present at QA site, forming semiquinone, and then the semiquinone transfers the electron to another quinone molecule present at the QB site. Then the QB, that is the quinone molecule, accepts 2 protons from the stroma and becomes reduced to plastohydroquinone, that is PQH2. This is how the electron gets transferred from chlorophyll A molecule to PQH2. Now, since the electrons or since the chlorophyll A molecules at the reaction center are deficient of electrons, so they will try to gain electron from some other source. So, who is the source? Water serves as the electron donor. The water is becoming oxidized with the help of a water oxidation complex present on the luminal site. So, this results in the evolution of oxygen. PQH2 on the other hand diffuses into the thylakoid membrane. There it goes towards cytochrome B6F complex. Cytochrome B6F oxidizes it and then the electron is transferred to plastocyanin. From plastocyanin, electrons get transferred to photosystem 1. The overall net reaction occurring at photosystem 2 is 4 molecules of P680 plus 4H plus 2 PQB plus 4 photons of light is producing 4 P680 oxidized, that is plus 2 pQbH2. This 2 pQbH2 goes towards cytochrome B6F. From cytochrome B6F, they goes towards plastocyanin and then further on to photosystem 1. In the photosystem 1, the chlorophyll A molecules or the special pair of chlorophyll molecules present in the reaction center is P700. Why 700? Because this chlorophyll A molecules are able to absorb photon of light at a wavelength of P700 nanometer, that is far red light. After it absorbs far red light, it again becomes excited, moves to the reduction potential with a lower reduction potential, and then it gives away the electron to a series of iron sulfur proteins, finally to ferredoxine, and from ferredoxine to NADP+, producing NADPH. So, the end result of photosystem 1 is the production of NADPH. The end result of photosystem 2 was PQBH2. So, this is how the photochemical events occurs at the two photosystems. The two photosystems are connected by mobile electron carriers as well as with the help of cytochrome B6F complex. So, in the net result of this Z scheme is the photosystem 2 is a strong oxidant and photosystem 1 is a weak oxidant and a strong reductant. Photosystem 2 can oxidize water, photosystem 1 cannot oxidize water. Photosystem 2 results in the evolution of oxygen and PQH2, whereas photosystem 1 oxidizes PQH2 and it results in the production of NADPH. So, this is how the comparison between photosystem 1 and 2 can be done. As well as there is a change or there is a difference in the wavelength of light absorbed by the each photosystem. Photosystem 2 absorbs light at red light, particularly at 680 nanometer. Photosystem 1 absorbs light at 700 nanometer. Now, with the help of Robert Hill, first discovered the photolysis of water. He found that during the light reactions of photosynthesis, there is evolution of oxygen. And what is the reason now? That the oxygen evolving complex associated with the photosystem 2 is the main key player behind photolysis of water. That is how it is done. So, let us come to oxygen evolving complex. Oxygen evolving complex present on the luminal side of photosystem 2. So, if you look into the structure of oxygen evolving complex, it is nothing but a cluster of manganese, calcium and chloride ions. There are 4 manganese ions present in different oxidation states, and these manganese ions helps in the extraction of electrons from water. Now, let us see what happens. So, a photon of light falls on P680, P680 loses its electron and it becomes 4P680 plus. So, one photon of light can cause one electron transfer. So, 4 photons of light will produce 4 electron transfer and 4 molecules of P680 plus. Since P680 plus is deficient of electrons, so it will try to gather electron from a source. So, who is the immediate source? Tyrosine residue present in the subunit D1 of photosystem 2. So, tyrosine residue present in subunit D1 gives its electron and a proton and becomes a radical. So, 4 P680 plus 4 tyrosine residues will now form 4 P680 plus 4 tyrosine radicals. So, the tyrosine is now deficient of electron. So, from whom it will take the electron? It will take electron from the manganese cluster. The manganese cluster present in oxygen evolving complex. So, 4 tyrosine radical plus manganese complex, as I told you, the manganese complex is containing 4 manganese ions present in different oxidation states. So, the different oxidation states are of manganese ions is, it is present 3 molecules of manganese are present in +3 oxidation state, whereas 1 molecule of manganese is present in the 4 oxidation state. This state is known as the S0 state. Now, with an absorption of photon of light, so S0 will become transformed to S1. During the process, one electron will be taken from this manganese cluster. So, it will form S1 states. This manganese cluster S1 on further absorption of light energy will again become 1, or it will give away 1 electron, and it will enter the S2 state. From S2 state again there will be absorption of a photon and the transfer of an electron. So, manganese ions or the manganese cluster will enter the S3 state, and the S3 state here it is entering the S4 state. So, in the S4 state, the manganese ions are present in the highest oxidation state, and now they have the capability to oxidize water. So, during this process, the water will be oxidized to produce 1 molecule of oxygen. There will be 4 electron transfer to the tyrosine residue. From the 4 electron to the tyrosine residue, the electrons will flow towards the 4p680 plus, producing the electrons to the deficient reaction center. So, as I told you, 1 photon of light causes 1 electron transfer. So, 4 photons of light will be helpful in photolysis or in catalyzing the photolysis of water. That is, 4 photons of light will cause the splitting of 2 molecules of H2O to produce 1 molecule of oxygen and 4 H plus ions. This 4H plus ion will be passed into the thylakoid lumen, which will contribute to the protonomotive force. So, the oxygen evolving complex is one of the very interesting features of photosystem 2, and it has been assumed that this oxygen involving complex had become first associated with cyanobacteria millions and billions of years ago. Now, water is a very stable molecule, and to catalyze the photolysis of water, there are 4 photons of light are required. Now, further on, so this is how the oxygen evolving complex operates with the photooxidation of water. So, on the other hand, the photooxidation of water is causing liberation of oxygen. The electron transfer from photosystem 2 takes place and gives the electron to plastoquinone. The complete reduction of plastoquinone to reduce plastoquinol takes place with the help of 2 electron transfer and 2 molecules of protons taken up from stroma. So, when 2 electrons and 2 protons are taken up from the stroma, it causes the production of 1 molecule of PQH2. So, 4 photons of light will produce 2 molecules of PQH2. The reduced plastoquinone is a small molecule, and it will now diffuse into the thylakoid membrane, and from the thylakoid membrane it will now go towards the cytochrome B6F complex. So, now we move towards cytochrome B6F complex. Cytochrome B6F complex is a multi-subunit complex. It contains 2 B-type hemes and 1 C-type heme, which is referred to as cytochrome F. It also contains iron sulfur proteins, in which 2 iron atoms are held by 2 sulfur atoms. So, the cytochrome B6F complex is one of the key players, and it is known that many herbicides act at this cytochrome B6F complex and prevents the photosynthetic electron transfer occurring during the light reactions of photosynthesis. The cytochrome B6F, or another special feature of cytochrome B6F complex, is the Q cycle. The Q cycle, referred to as the Quinone cycle, is very important as it helps in the translocation of protons from the stroma into the lumen. So, let us move to the Q cycle, that is the Quinone cycle. So, cytochrome B6F, it catalyzes the electron transfer from plastoquinone to plastocyanin and couples this exergonic process to the translocation of protons across the thylakoid membrane. So, if you look into the reactions, so what is the reaction of the Quinone cycle? That is PQH2, 1 molecule of PQH2 plus 2 plastocyanin oxidized plus 2H plus stroma is producing 1 molecule of oxidized PQ plus 2 PC reduced plus 4H plus into the lumen. Now, let us move towards the cycle. So, the cytochrome or B6F complex contains, or there are 2 turnovers of the Quinone cycle. Now, within the cytochrome B6F complex, there are two types of electron flow. One, the linear flow, another is a cyclic flow. So, one molecule of PQH2 comes towards cytochrome B6F complex. The B6F complex has got two binding sites, one referred to as the QP site, another referred to as the QN site. The QP site is towards the lumen, the QN site is towards the stroma. The PQH2 comes and binds at the QP site. The PQ from PQH2, 2H plus moves towards the lumen. Now, there are two electrons, so one electron flows towards the linear pathway, that is through the iron sulfur proteins and then to the cytochrome F, and then it moves towards plastocyanin. Whereas the other electron flows from cytochrome B, and then from the cytochrome B it moves towards another plastoquinone molecule present at the QN site. So, thus the plastoquinone molecule accepts this electron and it produces the semi-quinone. So, the first turnover or during the first turnover of the quinone cycle, one molecule of PQH2 becomes oxidized, producing PQ. Another molecule of PQ becomes reduced to produce semi-quinone. There are two electron transfer, one moving towards the plastocyanin and another moving towards the oxidized plastoquinone. In order to reduce the semi-quinone, the second turnover of the quinone cycle takes place. During the second turnover, another molecule of PQH2 comes and binds the QP site. From it, the 2H plus are liberated into the lumen. PQH2 becomes oxidized. So, there are now two electron transfers or two electron flow, one flowing again towards the linear cycle or linear pathway towards the plastocyanin. From plastocyanin it moves towards photosystem 1, whereas the other electron flows from cytochrome B to semi-quinone, and then semi-quinone becomes reduced to PQH2 and takes up 2H plus ions from the stroma. So, there are two turnovers of the quinone cycle. So, two molecules of PQH2 becomes oxidized to produce one molecule of PQH2 and a translocation of 4H plus into the lumen. So, this is the net result of the quinone cycle. This is an exergonic process and it couples the translocation of 4H plus from the stroma into the lumen. Now, we had seen earlier that photosystem 2 produces two molecules of PQH2. So, during the quinone cycle, one molecule of PQH2 is producing 4H plus ions translocation. So, two molecules of PQH2 will produce 8H plus ions or translocation of 8 protons from the stroma into the lumen. So, this will produce a protonmotive force and this will help in the synthesis of ATP. From plastocyanin, the electrons flows towards photosystem 1. So, plastocyanin is the mobile electron carrier, which is a small copper containing protein, water soluble in nature, and transfers electrons from cytochrome B6F towards P700. This protein is present in the luminal space of the thylakoid membrane. It occurs in certain green algae and cyanobacteria and so on. Let's now come towards the reaction center of photosystem 1. In the reaction, so plastocyanin comes and delivers the electron to P700 to oxidize P700 because a photon of light is absorbed by chlorophyll A molecules at 700 nanometer, becomes oxidized. So, now the plastocyanin is coming and transferring this electron to the oxidized P700 plus. From P700, the electron flows through series of electron transport carriers or series of electron transfer reactions, that is mainly A0, A1, and then it moves towards the iron sulfur proteins and finally it moves towards ferredoxine. Ferredoxine is a strong reductant and it accepts the electron from the reaction center of P700. From ferredoxine, it moves towards NADP+. The enzyme is a flavoprotein containing FNR. FNR stands for ferredoxine NADP+ oxidoreductase. So this enzyme reduces NADP plus to NADPH plus H plus with receiving electrons from ferredoxine. So we had started with a pair of water molecules, 4 electrons producing 2 molecules of PQH2, and this 2 PQH2 molecules will now finally produce 2 molecules of NADPH plus 2H plus. So these are the end products of light reactions of photosynthesis. 1 molecule of oxygen and 2 molecules of NADPH plus 2H plus. So this is how the non-cyclic electron transfer takes place during the light reactions. So this is with the help of this light reactions or with the help of this electron transfer, it helps in the production of ATP. So let us now conclude. So in this session, we saw an interesting or two interesting phenomenon occurring during the light reactions. The first one is the oxygen evolving complex, which results in the photolysis of water, and the oxygen which we are now breathing in is due to the result of the reactions occurring at oxygen evolving complex. The second one is the Quinone cycle occurring at the Cytochrome B6F complex, which results in the Protonmotive force production. So photosynthesis is a marvelous discovery which helps us to understand how the living beings, or especially the phototrophic organisms, they capture the light energy and how do they convert it into the chemical energy. Thank you.